Hello and welcome to Principles of Mathematics Lesson 2. We're going to continue our explorations with patterns in this lesson, and we should be able to um, find patterns and determine if they hold. We're going to look at deductive and inductive reasoning and when to use them. We're going to also look at different types of sequences such as arithmetic, geometric, and Fibonacci. Then once we get familiar with some sequences, we're going to try to see if we can find the nth term, which is basically a general term of some sequences. And for sequences that fall into neither arithmetic nor geometric patterns, we're going to see if we can use differences between terms to come up with some kind of a pattern. First, we'll look at a couple of situations in which it looks like a pattern exists, but we're going to learn to be very careful about jumping to conclusions about patterns. For example, if you look at what we have going on here, notice that we see a pattern of natural numbers increasing on the very left. In here in the middle we start with 0 times 9, then 1 times 9, 12 times 9, etc. So you see the 9 doesn't change as far as a factor in this middle part, and for each new term we have basically an addition of one more digit starting with the 1, then we have 1 2, then we have 1 2 3, 1 2 3 4, and in each case that factor on the left is being multiplied by a 9, and we get this interesting results on the right side which indicate a pattern. And of course this pattern seems to hold for a while at least, but further exploration will show that this pattern does not exist forever. In fact, if we look at this particular sum in that sequence, for example, we have 13 plus this goes all the way till 12, 1 2 3 4 5 6 7 8 9 10 11 12, and then you multiply that by 9. Notice we don't get that nice pattern of all ones, so the pattern definitely does not continue forever. As a matter of fact, it turns to break down once any of the digits that have already been used, like 1, is repeated. So we want to be really, really careful and not to jump to conclusions about the existence of a continuous pattern in these kinds of problems. The kind of reasoning where we basically look at some specific observations and try to find a pattern and make a generalization is referred to as inductive reasoning in mathematics. We hinted at it in our last lecture, and sometimes when the pattern does seem to hold, it leads us to come up with a conjecture, which is a statement that is considered to be true but hasn't been proven. Now, should we be able to prove it, then we'll be able to kick into deductive reasoning mode, which is we'll be able to use that general fact which has been proven to then reach some conclusions about any specific results. So remember, reasoning from specific to general is called inductive reasoning. Reasoning from general to specific is called deductive reasoning. Now, if a pattern or a statement or a conjecture does happen to be false, then oftentimes the method that we use to show that it's false is by using a counterexample. For example, we saw one just a minute ago right here. When we saw this could be thought of as a counterexample for the fact that the pattern that we had seen on the previous slide does not hold forever. Here's another tempting conjecture. Um, Here we notice that if we take a circle and then take 2 points on that circle and connect it with a straight line, we break the circle up into two regions. Then we notice that if we do that with 3 points, we end up with 1, 2, 3, 4 regions within the circle. And these are disjoint regions, right? They have no points in common. Now, it looks like when we do it with 4 points, if you count the regions, you'll see that you end up with 8 regions. There seems to be a pattern, right? Notice that the pattern would be 2 to the 1 regions here for 2 points, 2 to the 2 regions or 4 regions for 3 points, 2 to the 3 regions or 8 regions. Remember, 2 cubed is 2 times 2 times 2, so that's 8. 8 regions, right? So this looks to be a pretty reasonable conjecture at this point, because basically for the number of points, we notice that the number of regions will be 2 to the power of 1 less than the number of points. So here we had 2 points. What's 2 minus 1? That's 1. Here we had 3 points. So 2 to the power of 3 minus 1, that would be 2. Here we have 4 points. So 2 to the power of 4 minus 1, which is 3. However, if we continue, and we don't even need to go that far to find a counterexample, because if we just go to 6 points, now this is quite elaborate, so you have to be careful and label these very carefully and kind of methodically. Notice 1, 2, 3, 4, 5, 6. You work your way on the outside, then you go one level inside, etc. So if you count them, you actually realize that according to the proposed conjecture, there should have been 2 to the 6 minus 1, which is 2 to the 5, which is 32. Remember, 2 times 2 times 2 times 2 times 2. That's 4, 8, 16, 32, right? So you would expect there to be 32 regions, where in fact, if you count them, you'll realize that there are 31 regions. So this would be considered a counterexample for the conjecture that if you divide a circle using n points, then the number of regions within that circle would be 2 to the n minus 1 points. So we want to stay away from that conjecture. Remember, in mathematics, if there is even a single counterexample, we totally throw the idea away because it's not one we can rely on. We have a very high standard of what is true in mathematics and what holds, and the standard is that it should never fail. So even if it fails one time, we no longer consider it to be a viable fact. All right, next we want to look at some sequences. A sequence is an ordered arrangement of numbers, figures, or objects. They usually are classified by their properties. And one of the first types of sequences that we're going to study is what's called an arithmetic sequence. An arithmetic sequence is one in which each successive term is basically obtained from the previous term by addition or subtraction of a fixed number. Now, here's a very simple arithmetic sequence. Notice you start with a 2. So if you want to make a table, the first term, notice, is 2. The second term is a 5. Third one is 8. And so forth. So fourth one is 11. Notice each term is 3 more than the previous term. So 8 is 3 more than 5, 11 is 3 more than 8, etc. So this relationship between any two terms is important, but it would be great if we could find the relationship of all the terms to that very first term, because then we could come up with a nice definition for the general term of this sequence. So notice that the second term can be thought of as the first term plus that difference, which is called the common difference. Now, the question is, can I write the third term also in terms of that first term? And I noticed that I can. I would just have to start with that first term and then say add that to two of those common differences, or 2 3s, right? And notice we can do that with 11. We can say that's 2 plus 3 of those common differences, right? So by the way, notice we can even do that with the very first term. We can say that's 2 plus none of those common differences, or 0 of them, you see? And this second one, we can also say 3 times 1. By doing this, we help ourselves find the general term of this sequence, which we usually refer to as the nth term. We notice that all the terms start with 2, and we're going to be multiplying 3 by some number which is hopefully related to the term number, right? Notice that for the third term we need to multiply by for the fourth term we need to multiply by 3, so that's 1 less than 4. For the third term we need to multiply the common difference by 2, which is again 1 less than the term number. And notice that also works with the second term and the first term. So here we're going to say 3 times n minus 1. And we generally refer to the nth term as an, like so. So notice that the 3 here is what we call the common difference. We denote it with a D. And the first term here we refer to as A1. So now we can generalize this for any arithmetic sequence in which we know the first term and the common difference. As long as we know that, we can find any term of that sequence by using this simple and powerful formula. So take a look at that, make sure you absorb it and you understand it based on this simple example before we proceed. Notice that in this example, we have a graphic example of an arithmetic sequence. For each term of this sequence, we could, so let's say term number and then the term itself. So if the term number is 1, meaning the first term, you have how many matchsticks? Basically, we have 4 matchsticks, right? For the second one, we notice that we have 2, 4, 6, 7, right? For the third one, if you count it, you'll see that it's 10. For the fourth one, we notice that we have 13. So we can do a similar thing we just did on the previous slide with this. Notice this is like saying 4 plus 3 times 1. This is 4 plus 3 times 2. This one is 4 plus 3 times 3. the very first one itself was 4 plus 3 times 0, right? So you can see that the nth term of this sequence, an, is going to be 4 plus 3 times n minus 1. All right, so there we have the general term for this particular sequence. Sometimes they give us the nth term of a sequence and they want us to go ahead and find some values of the terms based on that definition. So here they tell us that the sequence is given using this formula. So for the first term, a1 is going to be 4 times 1 plus 3, right? For the second term, remember, so we often refer to this one as a1. This becomes a2. This becomes a3, etc., right? a4, that's just the fourth term of the sequence, etc. All right, now notice for the second one, it'll be 4 times 2 plus 3, etc., and on and on. So we can see this does lead to a arithmetic sequence where the common difference is 4, right? To get the common difference of an arithmetic sequence is one of the simplest things there is, because all you have to do is you have to subtract any two consecutive terms and you'll get the common difference. Here we have another sequence that's defined using this particular equation, an equals n squared minus 1. Notice that if we run through the values of n, the first term is going to be 1 squared minus 1, which is 0. For the second term, we plug in 2 for n, so we get 2 squared minus 1, which is 3. For the third term, we plug in 3, we get 3 squared minus 1, so that's 9 minus 1, which is 8, and then on and on, right? So we get 15. Notice this is not an arithmetic sequence because we don't have a common difference. The difference between these two terms is 3. Between these two, it's 5, and then 7, etc. So this is not considered to be an arithmetic sequence. Here we have an example from chemistry. In this diagram, we see the molecular structure of a class of compounds called alkanes, a class of hydrocarbons or hydrocarbons, and C represents a carbon atom here, and H represents a hydrogen atom. And when you see these connectors, that is indicating a chemical bond. So when you see, for example, CH4, we don't often write the 1, but this means there is 1 carbon atom and 4 hydrogen atoms, right? Notice that the next item in this sequence, another one of those visual sequences, has 2 carbon atoms paired with 6 hydrogen atoms. Basically, notice that each of the carbon atoms gets paired on the top and below by hydrogen atoms, and then there's going to be 2 on the side. So in each case, notice that the number of hydrogen atoms is going to be twice the number of carbon atoms, and then add another 2 for the sides, right? Same here, notice. So 3 carbon atoms, each gets paired with 2 hydrogen atoms above and below, and then 1 on each side. So again, so notice the relationship. So here for the first one, right here, notice that the number of hydrogen atoms is going to be 2 times the number of carbon atoms, and then add another 2. For the second one, notice the number of hydrogen atoms again is going to be 2 times the number of carbon atoms, and then add another 2. For this one, the number of hydrogen atoms will be 2 times the number of carbon atoms, which is 3. and then add the 2 on the sides again. So, and doing that, we get this sequence, right? So obviously, if this pattern continues, if a particular compound has 100 carbon atoms, it should have what? Twice 100 and then add 2. So 202 hydrogen atoms. What about a general term? Notice for any given number of carbon atoms, the number of hydrogen atoms can be found by just plugging into this expression, 2n plus 2. All right, so the alkane with 100 carbon atoms has a name. It's called a hectane. How many hydrogen atoms will it have? Well, remember, this is the number of carbon atoms, and we already saw this as part of our table on the previous page. And if you recall, it's going to be 2 times 100 plus 2, or 202 hydrogen atoms. All right, here we have another example of an arithmetic progression in the context of a theater. We have a theater set up in such a way that the first row has 20 seats, and then each consecutive row will have 4 additional seats. And we know that the very last row has 144 seats. So the question is, how many rows are there in the theater? Now, we could just jump to the equation that we know to exist for an arithmetic progression and determine what each of the values are, or we could do a little bit of exploring before we do that. I always encourage that because it gives you better intuition for what's going on rather than just plugging into a formula. Now we do know the formula for an arithmetic progression or an arithmetic sequence. In other words, the formula that gives us the nth term of such a sequence. But let's see what a few of the members of that sequence look like. So if we just set up a nice table, I want you to really get comfortable with setting up tables because they can be of tremendous help in mathematics. So let's set up our table like this. We're going to talk about the row number and the number of seats. Now we know that the first one is going to have 20 seats, right? And the second row is just going to add 4, right? So it's going to be 20 plus 4 times 1, which is 24. Can we write the first rows number of seats using this kind of a setup? Pause the video and think about it and see if you can do that. Write it in this format. All right, I think hopefully you know that you can always write this as 20 plus 4 times 0. Okay, so what would the third row represent as far as the number of seats? Well, that would be 20 plus how many of those 4s? We have to add 2 4s now, right? So we get 28. Now we can almost guess the general pattern already, right? We know that the nth term of this sequence is going to look like this: 20 plus 4 times, be very careful, it's not 4 times n, because for the third row it was 2 that you multiplied by. For the second row it was 1. For the first row it was 0 that you multiplied by 4. So each time it's 1 less than the row number, right? So 4 times n minus 1. Okay? And what we're interested in knowing is how many rows would correspond to correspond to 144, right? So basically, our equation is going to look like this. 144 equals 20 plus 4 times n minus 1. Now, we could have kind of jumped to this from the get-go because we knew that we have an arithmetic sequence. We knew that the first term, a1, is 20. Because each row adds 4, we knew that the common difference is 4. And we knew that what we're looking for is the scenario in which the number of seats, which is represented by an, turns up to be 144. So, but notice that when you go through this kind of a business, you get a much, much better sense for the problem than just jumping to this formula. All right, so now, of course, as you get more and more comfortable with mathematics, jumping directly to this will become like second nature for you. And at that point, it's okay to jump directly to that. But until we get there, it's always good to have a little bit of context and a little bit of analysis before you get to the formula. All right. So now all we have to do is solve this simple equation. So we have 144 equals, as always, if you think you know what to do next, pause the video, go do it, and come back. That's how you learn mathematics, by participating. All right, so let's assume you did that. So we get what? 20 plus 4n. Remember, we're going to distribute the 4 minus 4. So we get 144 equals 4n plus 16. Now we'll subtract 16 from both sides. So here we'll get 128 equals 4n. So now we divide both sides by 4. And we end up with n equals to, now here's one of those scenarios where most people may jump to their calculators, but if you really think about it, you don't really need to, because you can cleverly break 128 up into 120 plus 8 divided by 4, and I think you can easily handle 120 divided by 4, which is 30. And we can also easily handle 8 divided by 4, which is 2. So we get what? We get 32. So the theater had, remember, at the end of these problems, you always want to answer the question. So we can say the theater has 32 rows, like so. All right, so take a look at it and make sure you're comfortable with it. Redo it if necessary, and then join me as we proceed. All right, next we want to look at a famous sequence called the Fibonacci sequence, and it's defined using this formula. Basically, the nth term of the Fibonacci sequence is the n minus 1th term plus the n minus 2th term, right? So what does that mean? Notice that first of all, n would have to start with 3 and then move on to 4, 5, etc. So if you just plug in some of these values, everything will make sense. For example, starting with n equals 3, this tells me that the third term is going to be f. Remember, n is 3, so n minus 1 is going to be 2, right? So it's going to be f2 plus and n minus 2 is going to be 3 minus 2, which is 1, f1. So it means the third term is the sum of the first two terms. Is that true? Do note that some textbooks start this sequence with a 0, because that would also hold and be true. So because 0 plus 1 is 1, right? But in this case, in this book, they didn't, so we'll stick with this example. So notice that the third term right here, 2, is that actually the sum of these two terms, the first and second? Yes, 1 plus 1 is 2. Now look at, go to the next term, the fourth term, right? Let's look at what this translates into for f4. Well, f4 would have to equal, what's 4 minus 1? 3. And 4 minus 2 is 2. So it would be f3 plus f2. Let's see if it's true. So the fourth term is 3. Is that equal to the sum of the second and third terms? Yes, it is, right? Notice, take any term in the Fibonacci sequence is going to be the sum of the two previous terms. All right. Now, you may be thinking, well, that's great, but how do we use that? Well, it actually turns out in some really amazing places in nature. If you do a quick search on Google for the Fibonacci sequence in nature, you'll see some beautiful examples of where this actually pops up in nature. Before we leave the discussion of arithmetic sequences, I wanted to go back to our first encounter with them and remember how we came up with the formula for the nth term, etc. Now, one thing of interest is, why are they even called arithmetic sequences? Well, as it turns out, if you look at any three of the terms in an arithmetic sequence, the middle one actually turns out to be the arithmetic mean of the other two. So, for example, take these three, right? Notice that if you take the arithmetic mean of 5 and 11 is 5 plus 11 divided by 2, right? It's also known as the what? The average, right? Of those two numbers. Notice that that gives us 16 over 2, which is 8, all right? And you can do that with any three numbers in this sequence. And we'll look at these three, for example, right? So notice that you can take 8 and 14, find the average or the arithmetic mean, and you end up with 22 over 2, which is 11. It's always good to question why, you know, certain names, etc., appear in mathematics. It always gives you greater depth into why we're doing something rather than just taking your instructor's words for it or taking some book's words for it, etc. All right, so with that, we can go ahead and leave arithmetic sequences for a bit and learn about a different kind of sequence called an geometric sequence. By the way, arithmetic sequences are also known as arithmetic progressions. And the same goes with geometric sequences. They can also be thought of as geometric progressions. Okay, so whereas an arithmetic sequence is obtained by starting with some term and then adding a constant to get each of the next consecutive terms. In this case, with an arithmetic sequence, what we do is we start with a first term and then we multiply rather than add or subtract. We multiply by a constant term or a constant number to get then each next term. So for example, here notice we start with a 2. That's going to be our initial term, which is referred to as a in the case of an geometric progression. And then notice we multiply 2 by 3, we get what? We get 6. Then we take 6 and multiply it by 3, we get 18. Take 18, multiply it by the common by the ratio, and we end up with 18 times 3 is 54, etc., etc. Okay, so why called a geometric sequence, right? I mean, it looks pretty algebraic to me, doesn't it? So it's because of the history, right? It actually right here you can see the geometric connection here, because if you take a right triangle and drop a perpendicular from the right angle to the hypotenuse, remember the largest side of a right triangle is the side opposite the right angle, and it's called the hypotenuse, right? Now, this length here, which we refer to as the height of this triangle, if this is considered to be the base, can be easily shown to be the square root of the product of these two pieces that it breaks the hypotenuse into. So again, if you have had any algebra at all, you can follow along in this very, very simply. We know that the hypotenuse squared is equal to the famous Pythagorean theorem, right? Notice that the hypotenuse here would be p plus q, right? And we know that according to the theorem by Pythagoras, the length of the hypotenuse squared is equal to the sum of the squares of the two legs, right? So that's where this that's all this is claiming here. So if we just expand this using algebra, we get p squared plus 2pq plus q squared. On this side, we're going to replace r squared by another application of the Pythagorean theorem, right? Notice this itself is a right triangle. In this triangle, r is the hypotenuse. So we know r squared is going to be h squared plus p squared, right? So that's what we replace r squared with. And this is another right triangle in which s squared is going to end up being h squared plus q squared, correct? So notice that the p squares here are going to cancel out by we just subtract p squared from both sides, and so will the q squares, right? Just subtract q squared from both sides. So you end up with 2pq equals 2h squared, because there's one h squared and there's another, right? Now divide both sides of that by 2, you end up with h squared is equal to pq. So therefore h is just going to be the square root. You know, we just take the square root of both sides at this point, and we realize, or a more accurate thing to say actually would be that we apply the square root property, and we end up with h equals the square root of pq. So this right here, h, is called the geometric mean of p and q. All right, so if you have any two numbers, a and b, the geometric mean is going to be the square root of their product. And that's the reason for the name geometric sequence or geometric progression, because if you remember, we did that with arithmetic sequences. We realized that if we take any 3, right, then the middle term was going to be the arithmetic mean of the two other numbers. But in this case, as it turns out, if you take any 3, the middle term, the middle one, is going to be the geometric mean of these other two. So let's see if it works. Is 6 the square root of 2 times 18? Well, notice this 2 times 18 is 36. So 6 does indeed equal to the square root of 36. So it checks out. Try it with any other triple in this sequence and you'll come up with the same result. So for example, you can try it with 54, 18, and 162. Let's bring up a calculator and we'll use that. So if what we're saying is true, then if we take the square root of 18 times 162, think about it for a minute. What do you think that should end up being? All right, so before I hit enter, I think you should have the answer, and it should be exactly the middle term. Okay, so this is why we call these geometric sequences rather than arithmetic sequences. It has to do with the concept of geometric mean. Make sure to get comfortable with this concept and absorb it before we proceed. All right, before we go on, I want to quickly remind you of what the definition of a to the power of n means. And all that means, remember, is basically use a in a product n many times. That's all that means. So if you write, for example, 3 to the power of 4, that just tells you, hey, use this number, which is called the base, and this other number is called the exponent. So you're going to use the base how many times? As many times as the exponent. So like that. And of course, you can quickly do this by realizing that's a 9 and that's another 9. So it's going to be what? 81. Now, if n is 0 and a is not 0, then a to the 0 is defined to be 1. Now, when we get into some of our rules of exponents later on, we'll get a better feel for why that's true, okay? But remember that this only works if the base is not 0. 0 to the power of 0 is undefined. So, and we'll also get a feel for why that could be true as well. So, but that comes a little bit later. All right. All right, on this page, if you notice, we have two sequences of some very familiar looking objects. This one is obviously triangular in shape, and this one, if you see, they're squares, right? So if you delve in a little bit, you'll see some interesting results. For example, if you look at the triangular numbers, let's talk about the term number. And the number of dots in the particular triangular formation. Now, for the first one, we know that it's just one dot, right? For the second one, notice that it's 1 plus 2 dots. Oh, I meant second term. For the third term, which is this figure, we notice it's 1 plus 2 plus 3, right? For the fourth term, 1 plus 2 plus 3 plus 4. This should look very familiar to you at this point. So the hint is, think of lesson number 1 and the famous mathematician Gauss, right? So I want you to think about that, and I want you to see if you can tell me how many dots will be in the 100th term of this sequence. Pause the video, think about it for a minute, and then come back. Okay, I think you can clearly see from the pattern for each term, we're going to start with 1 and then add each consecutive natural number until we get to that term number, right? So for this, we would start with 1 and then 2, add 3, all the way up to what? To 100. Now, do we know how to calculate that sum? Remember, that's the sum that Gauss's teacher wanted to keep the class busy with, and Gauss came up with the clever, quick answer for it. Now, if you recall, we actually ended up figuring out what the nth term would be, and that term was n times n plus 1 over 2. So for 100, it'll be 100 times 101 over 2. And if you recall, let's calculate it again. Memory is not a friend to be trusted that closely. So 2 and 100 are going to cross cancel, just give us 50. So 50 times 101. 50/50. So 5,050 dots in the 100th image in this sequence of images or triangles, okay? So that's that. Now here's another one, square numbers, right? Pause the video, see if you can do this kind of a table and tell me what you come up with when you are done. As far as the nth term of this sequence is concerned. All right, so I'm hoping you have something kind of looking like this. Term number, number of dots. First one, again, just 1. The second figure in the sequence has 4. The third one has 9, etc. I hope that you can recognize this as 2 squared, 3 squared, 4 squared, right? So remember, 1 itself can be thought of as 1 squared. The second term is 2 squared. The third term is 9 or 3 squared. Fourth term is 16 or 4 squared. So what do you think is going to be the number of dots in the nth term of this sequence? For each term, obviously, the number of dots is going to be the term number squared, right? So what will it be? N squared. So how many dots will there be in the 100th figure in this sequence of figures? That's easy too, right? It's just going to be 100 squared, which of course is 100 times 100. So a 1 and 1, 2, 3, 4 zeros. So there'll be 10,000 dots in the 100th term of this particular sequence. All right, so a couple of sequences involving figures. All right, make sure that you are comfortable with this before we move on. All right, for our last example, we're going to look at a sequence which is actually neither arithmetic nor geometric. Notice there is no common difference. All the differences are different. Here we have a difference of 1 and then 8 and then 15, etc. Nor is there a common ratio, like the ratio of 6 to 5 is not the same as the ratio of 14 to 6, etc. So it's neither arithmetic nor geometric. So what we can do is we can use a trick where we try to see if there's a pattern in the differences between the terms. Now, before you proceed with trying to do that, I recommend that you write these much more spaced out, kind of like this. All right, because it'll be much easier to work when you have enough space between them. All right, so we go ahead and proceed by finding the differences between the consecutive terms. So we can show that like this. We find the difference between these two, we know that's 1. Between these two, we notice that difference is 8. Between these two, the difference is 15, 14 from 29. Between these two, 29 from 51, that's 22. And between these two, we notice that it's 29. So while the original sequence was not arithmetic, we notice that the sequence of differences is arithmetic with a common difference of what? Think about it. Subtract any two consecutive numbers, right? And you get the same thing. In fact, the difference between these two is 7. Difference between these two is 7. So we see this, that the sequence of differences is arithmetic. So we know that this next difference is going to be 7 more, which is going to be what? 29 plus 7, that's 36. So in order to get the seventh term of the sequence, they're giving us 1, 2, 3, 4, 5, 6 terms. They just want us to find the next one, right? So we just have to add 80 to 36. And that, of course, is 116. All right, so that's a clever approach to a sequence that didn't have either arithmetic or geometric progression initially. All right, it of course doesn't always work, but there are scenarios where this can be a helpful technique. All right, so that's basically a wrap for the lesson. At this point, as our usual practice, we'll go ahead and take a look at some of the homework problems where I feel like a hint may be justified. Okay, so in this question, we notice that the numbers aren't following any kind of a arithmetic or geometric pattern, but the pattern tends to be circular. That's why they want you to use a traditional clock face to determine the next 3 terms. So I'm just going to copy this and we're going to take it into a whiteboard where we can paste items for simpler use. Okay, so notice here we have the original problem and we also have a clock to help us out. So let's look at these numbers and see if we can see a pattern on the clock. So we're starting at 2, moving 1, 2, 3, 4, 5, 6, 7 places to get to 9. Then we go 1, 2, 3, 4, 5, 6, 7 places to get to the 4 that comes after. And then you can see the pattern goes 7 more, you end up at 11. 7 more, you end up at 1, 2, 3, 4, 5, 6, 7 at 6, right? So if you go 7 more, you end up at 13, which you know is going to end up being 1, right? 7 more is going to take us to what? To 8. And 7 more will give us 15, which is, as you know, is the way military time refers to 3, right? So right there. So that's where those magic numbers come from. All right, so it's, you know, you can get a clock like this very easily, say at Wikipedia to help you out. Or if you just go to Google Images and do a search, a clock is plentiful. It's helpful to have one without hands so they don't distract you. Here's another problem, and it's one in which we have a what's called a cubic pattern, because if you notice, the first term is simply 1 cubed, right? So if we actually make a little table like we usually do, so the first term is 1, which we can think of as 1 cube. The second term is 8, which is of course 2 cubed. The third one is 27, which is 3 cubed, etc. So they want to know what is the least 4-digit number greater than 1,000. Now, if we keep going down here, we know that 1,000 is itself is going to be one of these numbers. Why? Because if you think about it, that's 10 cubed, right? So if this sequence goes on like this, what do you think the next item is going to be? Think about it and see if you can come up with an actual value like 1,000. And if you do, you'll realize that's nothing but 11 cubed, which happens to be 1331. Okay? So this next question wants to know what's the greatest 3-digit number in this pattern. Well, we know that as soon as we hit 1,000, we've entered the zone of 4 digits, right? So the greatest 3-digit number is going to be the term that comes right before that, right? Now notice 1,000 itself is what? Is 10 cubed. So basically we're looking for 9 cubed. So let's see what that is on a calculator. All you have to do is just take 9, raise it to the power of 3. And that's where you get your 729. And that's where that comes from. All right, for part C, we want to know what is the greatest number in this pattern that is less than 10 to the 4. So 10 to the 4 is, of course, 10,000, right? So 10 to the power of 4, 10,000. So we need to find a perfect cube, the largest perfect cube less than 10,000, right? Now, just thinking of your numbers that we're familiar with, we know, for example, if we take 20 and cube it, we get 8,000, right? So it seems like we can do better than that. So this is going to be a little bit of trial and error. Let's say I jump to 22, right? I've gone over, right? So what's the only possibility? It's got to be the one in the middle, right? Between 20 and 22. So if I take 21 and cube it, I should get the largest number in this pattern that is less than 10 to the 4. Okay? Now, if this pattern keeps going, what's cell A14 going to be? And of course, that's going to be what? 14 to the power of 3. There you go. So 2744. All right, so a little bit different, but not too far off, not so difficult that you shouldn't be able to understand it and figure it out. So just the most important thing in math is not to give up, because the answer is there. It just takes some patience. All right, next we look at a nice application of an arithmetic progression. We know that Joe's annual income has been increasing each year by the same dollar amount, which tells us it's an arithmetic progression. The first year his income was 16,200. The 12th year his income was 31,600. We want to know in which year the income was 35,800. So basically we do know that this is an arithmetic progression. So we recall the formula for an arithmetic progression. And if you remember, we have an equals a1 plus n minus 1 d. Now, in this case, we know that the future amount we're looking at the first time around is the 31,600. That's for A12, right? So we can say A12 equals A1 plus, remember n is 12, so 12 minus 1 is 11, so we get 11D. And just one second. All right, these touchscreen laptops are very touchy indeed. As soon as you know you've gone on to some other application. Anyway, let's continue. All right, so we get 11D, and now let's plug in. We know that in the 12th year it was 31,600, so we get 31,600 equals A1, which is the initial income, 16,200 plus 11D. If we just subtract 16,200 from both sides, we end up with 11D is equal to, we'll get some help now, 31,600 minus 16,200. So we get 15,400 is equal to 11D. And now all we have to do is divide both sides by 11 to get our common difference. That means the amount that is being added each year, the same amount, right? So so we're going to take that previous result and we're going to divide it by 11. So we end up with 1400. So D is equal to 1400. Okay, so this is a problem where we're going to apply the same formula twice, because now that we know D, we can easily find out in which year the income was 35,800, because we're going to use the formula again. Now, we don't know n, but we do know what we want an to be. We want that future amount to be 35,800. I moved that too far up. Okay, so we have 35,800 equals, A1 doesn't change, that's the initial amount, right? Plus n minus 1, and now we do know the common difference, which is 1400. So now we have to solve this equation. So 35,800 equals 16,200 plus, we're going to distribute the 1400 from the right. So we get 1400 n minus 1400. So if we combine these two like terms, we get ourselves 16,200 minus 1400, so 14,800. So we have 35,800 equals 14,800 plus 1400n. We'll go ahead and subtract the 14,800 now from both sides. And we end up with 1400n on this side. And for the other one, we get 35,800 minus 14,800, which gives us 21,000. Now all we have to do is divide both sides by 1400. And we end up with n equals, so now we just patiently take care of that division. So we're going to divide that result by 1400 and we get 15. So now we know that it was in the 15th year that the price, the income was 35,800. So not difficult, just requires patience, right? Because you have to apply the formula not once, but indeed twice. And you just have to be careful to use the right numbers in each application, and you'll be in great shape, okay? So make sure that you absorb that before we proceed. All right, with this one, I'm not going to do it for you. I just want you to notice that, again, here you have a circular pattern. So just keep that in mind. You're going around circles and you should be in good shape. This one is quite simple, so I'll leave that as is for you to figure out. Here's one to drive one crazy possibly, but it's one that you have to really think outside the box. What they want you to do is connect all these 9 points with just 4 straight line segments, and the trick is going to lie in truly thinking outside the box. In other words, it is possible to do as long as you extend some of the lines beyond this figure, right? That's the big hint. I'll give you one other big hint. I do want you to figure this out because it's kind of fun, but I recommend that you start with a diagonal line and then take it from there. That's the second big hint that's not given here. So give it a try, see what happens. If not, you can always come and see me in office hours or something and I can help you out. All right, here's a good problem I would like us to take a look at together, because it's something we hinted at when I was defining arithmetic sequences, and we even verified it for some terms. Now we can actually move on and prove it in this problem. The fact that if you have an arithmetic sequence and A, B, and C are members of that sequence, consecutive members of that sequence, then basically the term in the middle is going to be average of the other two. So let's see how we would go about actually proving this. They guide you through a couple of steps. So the first thing that you want to do is go ahead and list the 3 numbers A, B, C. Now, you know, because it's arithmetic, the sequence, the differences are going to be the same of any 2 consecutive numbers. So For example, the difference between these two will be the bigger number minus the smaller, right? So b minus a, and the difference between these two is going to be c minus b, right? Oftentimes, what you want to do is you want to get as much facts as you can without even looking at these choices. Because when you do that, you notice that you have the answer already. So notice, because it's an arithmetic sequence, the difference between these two is going to be the same as the difference between those two. Now, if that's too abstract for you and you don't see it, just do a few numbers. Let's say we do a simple arithmetic sequence like 2, 5, 8, right? Each term is 3 more than the previous one, right? So notice that 5 minus 2 is the same as what? 8 minus 5. So, and of course they're both 3, right? So anytime an abstract situation gets to you or bothers you, try a real situation, a more concrete example, and then you can see the generalization to the more abstract case. So now if we take this simple equation and we're trying to establish that b is the average of a and c, so we're going to take this and we're going to solve it for b. See if it becomes the average of a and c. So notice it's a simple equation to solve. What we're going to do is we're going to get the b's on the same side and get rid of anything else other than b on the left side. So we'll start by adding b to both sides. That brings us to 2b is equal to c. 2b minus a, pardon. Let's not forget the minus a. Is equal to c, because the b's cancel out here. Here we get 2b and we already had the minus a. So remember, we want to move the a to the other side, so we're just going to add a to both sides now. And we end up with, now the a is canceling out, so we get 2b is equal to c plus a, or a plus c, the same thing. So now we divide both sides by 2. And we end up with b is equal to a plus c over 2, which is exactly what we were hoping to accomplish. We were trying to show that in an arithmetic sequence, if you take any 3 consecutive numbers, the middle one is going to be the average of the 2 around it. And that's what we just ended up showing. A little glimpse of how we do mathematical proofs. So make sure that you can handle that on your own before proceeding. That, I think, is actually a good stopping point for us. I promise you the videos after the first one will be shorter. I did keep my promise. So please take your time to really absorb this before attacking the homework, and it should go pretty smoothly if you do so. So with that, take care of yourself, and we'll see you at the next lecture.